Hi, everyone. Thank you for attending today's session. My name is Trey Smith. I'm joined by my colleague, Amir Sam Tamahasbi. Both Amir and myself are data scientists at ExxonMobil, and today we'll be speaking about productizing machine learning pipelines with Databricks and Azure ML. Okay, for the agenda, we'll first start off by providing some motivation and setting the stage on the material that we shared in this session. Next, we'll provide an overview of the use case that will be implemented. Thirdly, we'll touch on some of the key learnings that we hope that you're able to take away from this session. And then finally, we'll jump into the tutorial. So it's well known that deploying machine learning applications into production can take a significant amount of time and also require additional resources and experience to design and implement. In order to address this, our team has been developing a series of repeatable patterns and frameworks that data scientists across our organization can leverage to jumpstart and accelerate productizing their AI application. These patterns and frameworks are essentially a series of code repositories that contain production-ready code that covers all aspects of the ML lifecycle. These repositories have been developed based on previous use cases and learnings that have been captured along the way. There are two main components of the repositories that we'll dive into more in the tutorial. First is the infrastructure code, which is code for various technology stacks. And secondly is business logic code, which can easily be substituted for the data science use case, such as computer vision, anomaly detection, predictive maintenance, just to name a few. But the idea here is that data scientists would spend more time here on the model development and training and less on the infrastructure code. One of the templates we'll talk about in this session consists of integrating Databricks, Azure Machine Learning, and Azure DevOps for a full end-to-end model deployment pipeline. The visual here illustrates how we'll be using Azure ML Pipelines to facilitate data ingestion, model training, and model deployment using Databricks as a compute target and ML flow for the model management. We will then bring this all together for the full CI/CD workflow with Azure Pipelines. The use case that we'll implement in this session is a deep learning computer vision task, in particular image classification. We'll demonstrate how the templates can easily be extensible to the deep learning libraries such as Tensorflow and PyTorch. The dataset that we'll be using is an open source cats and dogs image dataset. The idea here is, though, that this toy dataset can easily be substituted out for your actual use case. But nevertheless, this particular dataset consists of 25,000 images. Those images are currently stored in Azure Blob Store, and then we'll mount the Blob Store to Databricks Workspace to easily consume those images. And we'll step through configuring this step within the tutorial. So in terms of key learnings, it's broken up into three different categories. So starting off on the left-hand side with Databricks, we'll walk through setting up a custom Docker image for initializing your Spark cluster. Secondly, we'll demonstrate how to set up Databricks Connect for executing your Spark jobs from a local VM on the Databricks cluster. We'll then walk through setting up your deep learning models, how you can use Spark for parallelized grid search as an example, and then use an ML flow to log those metrics and parameters. In terms of the Azure Machine Learning, we'll walk through setting up the AML workspace, how you can configure your AML pipelines to facilitate the training and deployment steps. And then finally, we'll deploy the models as a web service with a custom inference script. Finally, in terms of the deployment, we'll step through setting up your Azure DevOps for the CI/CD workflow for code quality checks, automated unit testing, and then finally using the pipelines for the release setup for your test and production environments. With that, we'll go ahead and jump into the tutorial.
To begin this tutorial, I'd like to first start off by discussing our local environment configuration. First, we'll be using a Linux virtual machine in Azure for development. Secondly, we'll be using Python 3.7.5. Lastly, we'll be working in Jupyter Lab. This is optional as you can also use your favorite IDE or develop within the Databricks workspace. However, this setup works particularly well for us given our codebase heavily uses modularization. Also, this approach may work well too if there's a preference to develop with editors like Vim or Emacs. Next, we'll use PyInf for our virtual environment setup. There are other options for virtual environments that could be implemented here as well. For more documentation on configuring PyInf, please see the provided link for reference. Within the virtual environment, we'll be using Poetry for managing the Python dependencies. Poetry allows you to declare the libraries your project depends on, and it will manage installing and updating the libraries for you. It's also a convenient way to organize and install optional dependencies. Finally, with Poetry, packaging systems and dependency management in Python can be rather convoluted, and thus Poetry makes it quite easy to package up your project. This becomes very useful when you're uploading a wheel distribution to the Databricks cluster for the source code to be executed. We will discuss this further in a few moments. By default, Poetry creates a TAMA file within the project directory, which contains the install packages. As you can see here, we have a list of required libraries and several packages that indicate optional. The optional dependencies are only installed if the extras flag is passed. For instance, you could pass the extra name Databricks to install only the Databricks CLI and the Databricks Connect packages. This feature becomes very useful when you're moving between your dev, test, and production environments. One last note to make about the environment configuration is in regards to the project layout. As you can see here on the left-hand side, we have a hierarchy of folders within the project root directory. The ML Pipelines directory contains all the infrastructure code for this project. Within each one of these files, we have some customized wrappers around the Azure ML SDK. These scripts handle setting up the AML workspace, compute, and orchestrating both the model training and deployment pipelines. Secondly is a business logic code, which is contained within the source directory. Within each one of these directories contains starter code for the data ingestion, preprocessing, model training, and deployment stages. This setup enables the data scientists to easily plug in their own code for a given use case. Over the course of this session, we'll be going more into these files and walking through the code. So now that we discussed the project layout, let's now walk through setting up the infrastructure. So the first step is to create our Azure ML Workspace. And the Azure ML Workspace is a centralized place that contains experiments, pipelines to orchestrate model training and deployment workflows, model registry, and deploy models. The below screenshot shows the landing page of the AML workspace from within the Azure portal. And in the middle of the landing page, you'll notice an Azure Blob store, container registry, and key vault are automatically created and attached to the workspace. So you do have the option to attach an existing key vault, container registry, and Blob store if needed. So let's now circle back to the AML pipelines directory and execute the script to create our workspace. So from within workspace.py, we have a helper function to create the workspace using the Azure ML SDK. And so within this config AML workspace function, there's two main components is within the try and accept block. First of all, we'll use a workspace object to be able to determine if a workspace already exists, and if so, we can exit, but if not, we can use the workspace.create object to create this workspace by passing in the name, subscription ID, resource group, location, key vault, and storage account name. So now returning back to the notebook, we can execute the code block to create this workspace. And as you can tell by the output here, we already have a workspace that exists so that we can skip creating a new one. One additional note to make here is that we do pass in the environment name to be appended to the workspace name. And this is so that we can differentiate between dev, test, and prod workspaces. So the next step is to authenticate to the Azure ML Workspace. First, we will use AZ login to log into our Azure account. Next, we will connect to the created AML workspace by passing in a JSON config file. And this file contains the subscription ID, resource group, and the name of the workspace. This JSON file can also be downloaded from the AML workspace within the Azure portal. And this approach is only for development purposes. However, for production, we will actually use a service principal for authenticating. We can also connect to the Azure Key Vault from this workspace object as well. And this works particularly well if you're passing in connection strings or other credentials in the source code or notebook. Now that our workspace has been created, let's proceed with creating the Databricks cluster. So there are two ways that the cluster can be created. First, you can create a cluster from the Databricks workspace, or you can use the Databricks REST API library. We will use the latter approach here. And so the next steps, we'll create the cluster and have it initialized using a custom Docker image. The reason for this approach, it allows us to have more control over the environment and installed libraries. This approach integrates nicely with Poetry and helps ensure dependencies are correctly installed across the dev, test, and production cluster. It should also be noted that the Databricks container services will need to be enabled by your workspace admin for the custom containerization feature. So in step one, we'll first use the base image provided by Databricks and add several additional steps for installing dependencies and packaging the Python module. The base image we will use here will be the Databricks runtime dpfuse. And this image supports Python 3.5 and fuse mounts to the Databricks file system. So in the Docker file output below, the first half refers to the base image, and then below there are additional steps for creating the virtual environment, and then Poetry commands for installing and building the Python distribution. Just as a note, once modifications are made to your source code, you can rerun the build steps so that the image contains the most recent wheel file to be executed on the Databricks cluster. In step two, we'll use the REST API to create the cluster. In the next steps below, we will create a 4-node cluster of Spark Runtime 6.2. Also, both the driver and worker nodes will each have 8 cores and 32 gigs of memory. So the payload example shown here will be used when making the REST call to create the cluster. Note that the Docker image URL and credentials are also passed to authenticate to the Azure Container Registry. Next, the commands to build, test, and push the Docker image to the Azure Container Registry are shown in the following code blocks. Once the image is pushed to ACR, you can verify from the Azure portal that the image has been uploaded with the latest tags. So now let's run the code to create the cluster. First, we will set several environment variables and use an internal library called DB-API that contains some helper functions for creating the Spark cluster. As a note, this step can also be executed without this specific library. Now to check that the cluster is initialized correctly, within the Databricks workspace, you can now see the cluster is initialized using this Docker image. So later in the tutorial, we'll demonstrate how this step can be incorporated in the CI/CD workflow with Azure DevOps. Now that the AML Workspace and Databricks cluster are both created, we will next attach Databricks as a compute target in the Azure ML Workspace. So this step is necessary when running the Azure ML pipelines and executing the training and model deployment steps with Databricks as the assigned compute resource. Also in this step, we are not specifying the Databricks cluster ID yet. Rather, this will be set in the Azure ML pipeline stage later on. So in the AML pipelines directory, we will now call compute.py to execute this task. Within the script, we have a helper function that first checks to see if Databricks has already been attached as the compute target. If so, then we do not need to reattach and can exit. If not, we will use Databricks compute.attach configuration and pass the resource group name, Databricks workspace name, and the Databricks access token that can be created from your Databricks workspace. The last step is calling compute target.attach from the Azure ML SDK to attach the Databricks workspace. So returning back to the notebook and executing this code block to attach our compute target, we will see that the compute name Databricks CV dev-dev has already been attached, and then we can proceed. Again, you may want to provide an alias in your compute name which indicates the corresponding environment. To verify this step, we were able to see now from the Azure ML Workspace that indeed the attachment was successful given that the provision state has succeeded. So our next step will consist of mounting the Azure Blob store to the Databricks workspace. So recall that our image dataset has been uploaded to a container in Blob storage, and thus we will need to mount this container to the Databricks file system to be able to access these images. So to get started with this task in Databricks, it's highly recommended to handle keys with dbutils.secrets. So prior to mounting the data store, it's advised to add the connection string of your blob store as a secret in an existing Azure Key Vault, or you can also use the Key Vault that is attached to the AML workspace. Next, you can also create a scope in Databricks, which is a collection of secrets that are stored in the Key Vault and accessible by the cluster. The scope can be created by replacing the URL link shown here with your cluster hostname and organization ID, with the hashtag secret/create scope appended at the end of the URL. So upon creating the scope, you'll be prompted to enter the DNS name and the resource ID that can both be obtained from the Azure Key Vault properties in the Azure portal. So given that we are developing outside of the Databricks workspace, you can execute this mounting script shown here by copying it over to a notebook within your Databricks workspace and to execute. Note, this is only required to mount once, as all clusters in the workspace can consume this data depending on the access privileges that have been set. So our last step before moving into the model training stage, we need to set up Databricks Connect in order to execute Spark jobs remotely on the Databricks cluster instead of in the local Spark session. So for instance, this will enable us to convert a list of dictionaries containing hyperparameters into an RDD and call the map partition transformation to enable training several models in parallel with different tuning parameters. The model training is now being conducted on the Databricks cluster rather than locally. And so this screenshot demonstrates how the Spark job is invoked from this virtual machine and is executed now on Databricks. Now to get started with Databricks Connect, I would recommend referring to the documentation first. However, at a high level, the initial step is to uninstall PySpark if currently installed. Next, you'll need to ensure that Databricks Connect is installed in the virtual environment within the project. Secondly, you'll need to install the version that matches your cluster runtime. For example, we will be using Databricks Connect 6.2, given the Databricks runtime on the cluster is 6.2 as well. Next, you will need to run Databricks Connect Configure to set up the connection properties. You'll be prompted to enter the Databricks hostname, token, cluster ID, organization ID, and port. And this will create a configs file within your home directory. And to check the setup was properly configured, running Databricks Connect test should yield all tests have successfully passed. So to double check that this works, we can initialize a Spark session, and this would trigger the cluster to spin up if currently terminated. Or we could also use dbutils to list the files in the image container that we mounted in the previous step. So from the output here, we can view that the list of files from the image path, and thus this verifies that it works as expected. And so the last comment to make here regarding the development environment we will cover in the next steps. We will first test our preprocessing, model training, and model deployment stages using Databricks Connect. After the development code has been tested, we will then integrate with the Azure ML Pipelines. This approach allows us to easily isolate any issues with the source code and quickly resolve any bugs. So I'll now hand it over to Amir to discuss the preprocessing stage and to walk through the development of the CNN models.
In this part, I'm going to give you an overview of how we can test our source code in our pipeline. First, we need to have a data set to test our pipeline and our models. In this part, we have used the famous dogcat dataset from Microsoft, which has been used in Kaggle competition in 2013. This dataset contains 25,000 images of dog and cat, which been split into 50-50%. And we have employed this data. The data comes in one folder. However, since we want to perform our training of our models using batch normalization process, we need to split our data into train, validation, and test directories. And each directory would have like two subdirectories of dog and cat. In this part, we have used 80% of the data for the training, 10% for validation, and 10% for the data, for the testing the model, sorry. In this part, we can see the layout of our directories for the train, test, and validation part, and each of these folder contains two subdirectories as cat and dogs. This part would give us the ability to apply like image pre-processing, including resizing, normalization for the pixels, and augmentations. In this part, we have used the pre-processing module of Keras. However, you can use based on your use case using Pillow or CV2 modules in Python and probably the other libraries as well based on your use case. Please note that this is a just one-time process for the whole training part, which you have to do it based on your use case, and you do not need to repeat it each time. Here we can take a look at the 10 random samples of each directory. Here we have like a dogs, and after that we can see like the 10 random samples from our cat folders. Now it is a good idea to take a look at the pre-processing code for the image pre-processing part. First, we have like a train test split, as we discussed in the folder, and directories like segmentations and splitting the images into test, train, and validation sets. Here we have prepped the images to have the same like to the proper width and height. Here we have chosen like 200 pixels. And the point here is all these like a pre-processing part, it's been done in Databricks and using Spark. And here's like we parallelize the whole image pre-processing aspect. This is true. It's supposed to be done like at just this is one-time process. However, in this case, we can use Spark and the whole process could be scalable and we won't be worried about the size of the images. In this section, we are training multiple deep learning models to test that of our platforms and our pipeline. In this part, we have used Tensorflow and specifically with high-level API Keras, and we have also used PyTorch. The main idea here would be how to demonstrate our template can be extensible for implementing other deep learning libraries, and we can employ different libraries and run and train different models and use the Databricks as a cluster to train these models. For the TensorFlow part, we have used first a 3-layer vanilla CNN, as the benchmark of our models. And the whole idea of the whole implementation is like we have a parameter like number of rounds, which can be passed to each like the models we have trained, and indicating the number of models we can train at the same time in parallel. And these like hyperparameters of these models is a random combination of the hyperparameter set we have, and for each one, it's going to be a list of dictionaries containing these hyperparameters, which can be converted into Spark RDD format using map partition transformations. In better words, we would have one model per partition block, and that the whole process is going to be done in the Databricks cluster, and we are not going to use our virtual machine. This is, as we've shown here, the illustration of the VGG16 model, which we have used as a second case of our TensorFlow platform as a transfer learning model to see how this model can outperform the normal benchmark model we define as a 3 layers with convolutional neural network. This is the layout for our parameters dictionary example. The value is associated to each key, technically, which they are like a hyperparameters of our model, are randomly selected when generating a set of hyperparameters. For instance, if in our like a normal model we have a number of rounds of 2, which means 2 lists of dictionaries going to be randomly selected based on the all combination of like a possible combination of these parameters, and each of those like a dictionary is going to be changed to RDD format using in a Spark using map partition transformations. And based on that, these parameters are logged into our ML flow, and then the model with the highest test accuracy is going to be selected for that run. In this part, I would like to take a couple minutes to talk about the codes we have for TensorFlow and PyTorch. As you can see in the source directory here, if you go to the train part, we could see like the two main files for the TensorFlow and the Torch. If I go through the TensorFlow file, I can see that we have a function which has we defined a class for training the models, and then here's a part I talk about how that each number of rounds, which gonna talk about one dictionary of hyperparameters, which gonna be partitioned into different each block, and we can parallelize that process through Spark. This is the part we can have. It's the hyperparameter tuning can be applied using like a Spark-like parallelization, and we can train multiple models at the same time. After that, so we can take a look for each model as well. So for instance, if I take a look at the CNN we have for the TensorFlow, we have a class for data generator. And based on that, so we have a helper function which is going to take care of the pre-processing and any image pre-processing, any kind of augmentations we have involved. And then here's the part that go through our baseline CNN, which was 3 layers CNN, and we have a transfer learning as well, which we have used VGG and 3 layers of VGG models. We have the same, similar process for PyTorch as well. As you can see here, if you go back to the train part and for the torch part, you could see this file, which as you can see, this is like a similar parallelization applied here. And we have also applied here the same process for the data generation and pre-processing. And here the only difference would be the architecture of the CNN model, which is instead of VGG16 here, we have used ResNet 18, and we modified the ResNet which via batch normalization parameters. And this would like give us like a good opinion about how this like a process works. And then here we can see like the results for our Bayesian CNN model, and how when we applied our like a ImageNet on the model, we get a result, and how our like a result based on the PyTorch like outperformed the previous result.
Thanks, Amir. Now we'll discuss further how we're using MLflow for model management. With MLflow, we're able to track experiments for multiple model configurations, like the ones previously discussed. And this allows us to easily compare parameters and results across the different models. You may also use MLflow for model deployment, packaging your ML source code, and having a centralized model registry store to efficiently manage the model's full lifecycle. So for this example, we'll be using the MLflow tracking server hosted in the Databricks workspace. To connect to this remote URI, we would first need to pip install Databricks CLI. Next, we will then run Databricks configure and pass a profile name along with the token flag. You will then be prompted to enter the Databricks hostname along with the access token. And once installed, we can then set the tracking URI to Databricks:// the name of your profile. So moving forward, we will now be communicating with the ML Flow tracking server hosted remotely on Databricks. To see how ML Flow is implemented in this use case, let's take a look at the source code. Within the train directory, we can step into the log folder, which contains a script for recording the model results along with saving the model artifact. For example, let's take a look at the logtorch.py file. So in the do ML Flow helper function here, we can pass in a list of input parameters and the name of the experiment. Again, this setup can work for one model or log parameters for multiple models which contain different configurations. Next, the history variable defined here is just a dictionary containing the loss and accuracy scores for both the training and validation datasets for each epoch. We will then create an MLflow experiment name if one does not already exist. Next, we can iterate over a list of parameters such as the optimizer, dropout percentage, and the number of dense units for the hidden layer as an example. And then afterwards, we can loop over each epoch and log the training and validation loss and accuracy score. The final step here is to save the model by calling mlflow.pytorch.logModel. We can now return to the notebook and view how this looks from the MLflow UI hosted on Databricks. So here we have two experiments, one for Tensorflow and one for PyTorch. From the UI, we can view the date of the experiment and also the user who submitted the experiment. Additionally, we can view the log parameters and metrics for each run. Also within the UI, we can easily search for the top performing models based on a scoring metric, and we can also filter based on tags that were created in the experiment run. We can then step into each run and explore further metadata such as the plot shown here. We can easily plot for each epoch the accuracy and loss for both the training and validation datasets. Our next task is to automatically obtain the best model so that we can upload it to the Azure Container Registry. Given the ResNet 18 model using PyTorch yielded the best score, we will proceed with deploying this model over the course of the next few steps. From the MLflow UI, we can see the model artifact that we want to register in this screenshot. And the reason for this step is so that we can deploy our model as a web service in Azure using a custom inference script. An alternative approach is to use mlflow.azureml to deploy the model or deploy from an image. Please refer to the provided link here for additional documentation. To execute this step, in the deploy directory within the source code, we will step into main.py. Here we will call the getBestModel method to search for the best model in the PyTorch experiment. First, we will obtain the experiment ID and then pass the ID to the search runs function. We will next sort the scoring metric in ascending order and then take the first index of this list, which will contain the trained model with the highest accuracy score on the test data set. Returning to the notebook and running this code cell, we are able to obtain the best model. We can see the corresponding experiment ID and run ID from the PyTorch MLflow experiment. We will then download the model locally so that we can continue testing the deployment stage. We can download the model artifact from the MLflow tracking server by referencing the path to the artifact. Here we will plug in the experiment ID and run ID to the model path. Next, we will call mlflow.pytorch.saveModel to save the model to the local file system. We'll then register the model to the Azure ML model registry. Let's go back now to the main.py file in the deploy directory. Here we'll use the register model helper function, which takes in the workspace object, model name, and model path as inputs. To register the model, we will now use the model class from the Azure ML core library and pass in the respected inputs. So executing this code block, we can see that the torch CatDog model has successfully been registered. In the AML workspace within the Azure portal, we can see that our model has been registered, and now we can proceed with the model deployment. When your model is deployed, you'll be able to see the deployed web service under the Assets tab, Deployments, in the left-hand panel within the AML Workspace. Now let's step into the code to deploy our model with a custom scoring script. So back in main.py within the deploy directory, we will call the helper function deploy model and pass in the AML Workspace object, model name, deployment name, path for our inference script, and the number of CPUs and memory allocated to the web service. Next, we'll need to define the dependencies required for the custom scoring script. Here we'll be using Conda and only install NumPy, PyTorch, MLflow, and the Azure ML core library. Secondly, we'll also need to define the web service deployment configuration by passing in the CPUs and memory. For this web service, we will set the number of CPUs to 2 and memory to 4 gigs. These settings will vary depending on your use case. Afterwards, we will need to also define the InfraScript configs by passing in the path for the scoring file and also the Conda environment. Before moving ahead to the next step, let's take a look at the scoring script that we'll utilize in the deployment. In this file, first we'll initialize the model by getting the model path from the AML model registry, and then calling mlflow.pytorch.loadModel to load in our saved model. In the next function below, this will be invoked when making a post call to the web service endpoint for a model prediction. In this step, a serialized JSON object containing the input image pixels will be passed to the run function. We will then reshape the NumPy array into a tensor with 3 channels. Next, we will make a prediction and return the binary label either 1 or 0. Note this script is only for PyTorch implementation. However, a similar script is available to Tensorflow as well. Okay, returning back to the deployment script. We will now call model.deploy method and pass in the AML workspace, the deployment config, inference script, and the model object, pointing to the torch model we registered in the previous step. By default, this will pull the most recent model registered with this name. Last step is to also wait until the deployment completes before proceeding. Let's now execute this code block. From the output, a warning is thrown stating that the deployment name is not found and then proceeds. If it exists, then we will pull this web service down and replace it with the updated one. Note, this step takes a few minutes to execute. Once completed, you'll also be notified that the operation has succeeded. Now let's check to see if our deployment worked as expected. Here we'll randomly pull an image from the downloaded cat and dog sample test set saved locally. In this case, the image we're predicting is a dog. Next, we'll use OpenCV to read in the image and resize it to 224 by 224. Prior to making a prediction, we'll need the scoring URI of the web service when making the REST call. To do so, we can pass in the AML workspace object and deployment name to obtain this URI. Let's quickly take a look now at the score.py file within the inference directory. Here we'll call the predict method to make a post request to the deployed web service. To clean up the response, we will return cat or dog depending on the predicted label. As you can see, the model correctly predicted dog. Now that we have tested our source code locally and executed our Spark jobs remotely on Databricks, let's now integrate the training and deployment steps with the Azure ML Pipelines. As a reminder before testing the pipelines, you may need to update the Python wheel distribution if any changes were made to the source code. We can rebuild the image and push to the Azure Container Registry. This step ensures that our updated source code is being executed now on the Databricks cluster. Let's now briefly talk about the Azure ML Pipelines and how we will integrate with Databricks before jumping into the code. Azure ML Pipelines enables logical workflows with an ordered sequences of steps for each task of the machine learning workflow. In other words, we could have one pipeline with multiple stages, or have multiple pipelines with a single stage, or a combination of the two. Depending on your use case, there are a number of ways the pipelines can be configured. Within the pipeline, we will need to define a step, and there are many built-in steps available via the Azure ML SDK. For example, you can set up a Python script step, which runs a Python script and a specified compute target. For this example, we will use the Databricks step with Databricks as a set compute target. Given how our codebase is set up with Python modules, the Python script argument for the Databricks step will be set to the main.py files within the business logic code as the entry point. When you submit a pipeline, Azure ML will first check the dependencies for each step and uploads a snapshot of the source directory specified. Once the steps in the pipeline are validated, the pipeline would then be submitted. Also note when you submit a pipeline, Azure Machine Learning builds a Docker image corresponding to each step in the pipeline. And finally, running a pipeline will create an experiment within the AML workspace. And from here, you can refer to the output logs and additional metrics to monitor the pipeline run. So the last step after testing the pipeline is successfully completed, you can publish the pipeline and then invoke this pipeline to run either by a trigger or a scheduler. The pipeline we will now submit will consist of two steps within a single pipeline. The first step is to perform model training. Once model training is complete, the second stage will be to execute and deploy the best model from the model registry as a web service. Note to bypass a full train at this step for demonstration purposes, we will reference a sample dataset of 10 training and validation images. Let's now take a look at the infrastructure code to orchestrate this pipeline. Within the AML pipelines directory, let's step into pipeline.py. The first item to point out here is the base DB stage class. This is a custom class which is a template for the other pipelines to inherit from. This approach is particularly useful when there are multiple steps within the pipeline, and each step can inherit from the base setup. Within this class, the dbStep method initializes the Databricks step object from the Azure ML SDK. Here we'll pass in the Python script path, input arguments, compute target, and the cluster ID. The cluster ID here should point to the cluster in the appropriate environment, dev tester prod. The environment name can be passed as an input argument here as well. Next, we have several helper functions to submit and publish the pipelines. The final method here executes the steps for creating and running the pipelines. The first half of this function sets up the input arguments namespace, authenticating to the AML workspace, and initializing the experiment object. One of the main components of this function is to iterate over a series of objects corresponding to the ML stage, and then store these steps, which are then passed to the pipeline object to be executed. In other words, this step allows you to have multiple objects, one for each training and deployment. The approach presented in this example, we will just have one class, train and deploy, but contain two steps for this stage. Let's now take a look at train-deploy.py and see how this is configured. The train-deploy dbStage class inherits from the base dbStage as previously discussed. Within this class, we can set up the input arguments for each step individually, one for train and the other set of input arguments for deployment. Next, in the add method, we have two steps defined, a list of input parameters and the Python script path. Lastly, step 2 can only run after step 1 completes, meaning we cannot deploy the model until training has finished and the metrics are logged with MLflow. So returning back to pipeline.py, the last few lines of code here consist of validating the pipeline, and depending on the input action flag passed when invoking the script, the pipeline will either submit or publish. Returning to the notebook, we can now run this code block to submit the training and deployment pipeline. As you can see from the output, the first step, the model training, has completed. In addition, we can also see from the second step, the model deployment, it is also finished as well. And so for the complete log of this pipeline run, it can be obtained from the Azure ML Workspace, or it can also be obtained from the Spark UI on the Databricks cluster. The next two code blocks here are optional design patterns for the pipeline orchestration. This approach consists of two separate pipelines, each containing one step. Next, we can test the publishing of the pipelines. Before publishing though, let's disable the older pipeline and then replace it with the updated one. In step 2, this is the same step as the previous step when we submitted the pipeline. However, here we would just change the action flag to publish instead of submit. Once published, the pipelines will appear in the Azure ML Workspace. Also note that the publishing does not run the pipeline, only being triggered or scheduled. So the next code block here demonstrates how you can trigger the pipeline to be executed. Our source code in dev is now complete, and at this point we're ready to push up to the remote origin. So let's now switch gears and discuss the CI/CD workflow. I would like to preface that the remaining steps presented here are just one approach, as there are many variations that could also be implemented. Perhaps these steps do foster new ideas, or if unfamiliar with the space, the steps may provide an example to help build off of. As referenced earlier, we will be using Azure repos to host the Git repository for this project, and Azure pipelines to build, test, and deploy the CI/CD. Moving forward with the first step in the CI/CD workflow, the continuous integration phase. Each time a new feature or enhancement is added to the codebase, the data scientist will create a pull request to be reviewed before merging with the master branch. This pull request will trigger an Azure pipeline to perform an automated code quality check and robust unit tests. A policy can also be set to the master branch in Azure DevOps to ensure the build is successful before the merge with master can take place. Let's now take a closer look at the CI pipeline YAML file that will be executed once the integration pipeline is triggered by the open pull request. First, we will define the VM image with Ubuntu. Next, we will define the variable group that will contain our environment variables. Thirdly, we will set the pull request trigger. Here we will define the integration test pipeline to be executed only for our feature branches. Afterwards, we will define the Python version, 3.7. Following this step, we will then log into our Azure account with the service principal. Recall in the development environment, we were using the config.json file for authenticating. However, for the Azure pipelines and the release pipelines that we will discuss in the next section, we'll only be using a service principal account. Afterwards, we will then install the dependencies required for the unit test with Poetry. Following this step, we will first need to configure our Databricks profile, as we will be testing MLflow upon the best model in the unit test step. Next, we will then run AutoPep8 to auto-format the source code to PEP8 standards. This ensures our code remains consistent when multiple contributors are adding features and enhancements to the source code. We'll also run code linting with Flake8 to check for any syntax and styling errors within the code. Next, we'll run PyTest for testing the source code. These unit tests are within the test directory located in the project root. Note that the unit test implemented here is for illustration purposes and would need to be more extensive in practice. However, the unit tests are a critical part of the workflow to ensure the code is fully functioning as expected before promoting an application into production. The last two steps are then to publish the unit test results and also the coverage of those tests. Next, we'll create the pipeline in Azure DevOps. When creating the pipeline, we would then select using an existing Azure pipeline YAML file. We would then select the CI pipeline file to reference. Once the pipeline is triggered and completed running, we can view the job results. Here we can step into each task for the output log. It can also be used for debugging in the event one of the steps fails. As we can see from the screenshot, all steps defined in our YAML file have successfully completed. In Azure DevOps, we can also view the results of the unit test and also the coverage of those tests. Now to complete the pull request, we can see in the top right-hand corner that our pipeline has succeeded and has been reviewed. Therefore, this pull request can now be merged with the master branch, and we can move into the release stage for our deployment. The final section is now to discuss the continuous deployment with release pipelines in Azure DevOps. When the pull request was merged with the master branch in the previous step, this initialized the release pipeline to automate the model deployment into production. For more information on configuring releases, please see the provided link. But at a high level, to get started and to create a release, select Releases under the Pipelines tab in Azure DevOps, as shown in this screenshot, and then select New Release Pipeline. To begin with the release setup, we will use an empty job template. Next, we will configure the build artifact, which was created from the master branch trigger. We will discuss this step more in a moment. Here we will then enable the continuous deployment trigger, which will then kick off our test environment stage. After succeeding and approved, the model will be deployed into production. Within our test environment, we will create two stages. First, for Databricks, just like we did in Dev, we will build the Docker image to contain the updated source code and dependencies, and then push the updated image to the Azure Container Registry. This step is so that our test cluster pulls the most recent image when initializing. The second stage is related to submitting and publishing the Azure ML pipelines. We'll talk about both of these stages in a moment as well. Now let's briefly take a look at the Azure pipeline YAML file for the build artifact. Similar setup as before in the integration pipeline. However, this time we will set the branch trigger to master. Next, we will log into our Azure account, and the final two tasks are to create a copy of our source code, and finally, publish the artifact, which we will reference in the release setup. Circling back to the stage setup, each task within the stage will consist of adding a command line agent job as shown in the screenshot. Also, the defined stages run on an agent in an agent pool. In this example, we will run these jobs on Linux compute nodes. Next, our first task is to set up the test stages for Databricks. Here we'll have 4 tasks for building and pushing the updated image for the test cluster as we discussed earlier in the development environment. Moreover, each code block here will be its own individual stage with the execution script for the corresponding task as shown here. Lastly, note that we will need to set the working directory of the build artifact so that our path to the Docker file is properly configured. Similarly for the Azure ML side, we will set up our environment using Poetry install, and then submit the training and model deployment pipeline, followed by publishing the pipeline itself. Recall when we submit the pipeline, it executes the defined steps, while for a published pipeline, it can be triggered, such as a file uploaded to a Blob store, or scheduled on a defined cadence for the steps to then be executed. The last step here is then to disable the pipeline as it will no longer be in use once the test stage is complete. In this scenario, one of the reasons that Databricks and Azure ML stages are segmented is to help isolate any issues that may arise. Finally, for the production stage, the same tasks are executed as in the test. However, we will consolidate these steps into one stage. And the last note to make here is in regards to defining the environment variables. The Variables tab within the task configuration window, as shown here, allows you to easily assign the variables based on the environment it should correspond to. Once our release setup is configured, we can now save and use this release for the continuous deployment phase. As shown here, the master branch trigger executed the release phase of our workflow. At this point, the Azure Pipeline YAML file will be executed to build and publish the release artifact, which then kicks off executing the Databricks and Azure ML test stages as previously discussed. After test succeeds, we then have an option of setting up post-deployment approvals, such as a release gate, where someone like a project owner would have the final review prior to promoting to production. I would recommend checking out the documentation for more settings to configure your deployment approvals. Finally, once the tests have passed, our image classification model has now been deployed into production. So in conclusion, we have now demonstrated how to develop a machine learning pipeline which integrates both Databricks and Azure ML, and walk through how to deploy our toy example, a deep learning image classification model, into production using CI/CD. The idea for the framework presented here today is to be adopted as a starting point for other data science use cases to help enable the acceleration of deploying ML applications into production.
All right, thank you.